Hello everyone, I hope you're doing fine. Today in this lecture we're going to learn about section 4.5, which is concavity and inflections. And this section, together with the previous section 4.4, the extreme values, these two sections together will allow you to roughly sketch graphs of functions, provided that you can figure out the first and second derivatives of this function. In the previous section where we covered extreme values, you learned how to find local extreme values of a function, which tells you where there are bumps in the graph of the function, like local minimums, local maximums, little bumps. What you're going to learn in this section, concavity and inflection points, these will tell you how the graph of your function curves. What do I mean by this? Okay, let's say that you have a nice differentiable function. It is a graph. If you look at this curve, which is the graph of the function, there are two things that can happen. When you pick pretend that the graph of the function is not a line. That's going to be a degenerate case. When you pick two distinct points on this curve, which is the graph of your function, when you connect these, this line segment connecting these may stay above the graph, or it may lie below the graph. Okay, so as you can see from the picture, there are essentially two ways the graph of your function can curve. It can curve like this, and it can curve like that. And these this observation brings us to this observation suggests the following definition. So I'm just going to directly write down the definition of concavity without doing much definition. So let f be a function, let f be a differentiable function on an interval AB. We say that f is concave up on AB if this is a differentiable function, it's there on this interval, its derivative is defined, and if its derivative is an increasing function on this interval, we say that it's concave up. If its derivative is a decreasing function, then we say that it is concave down. So let's understand this definition. What does this really say? Okay, pretend that over here I'm gonna sketch the graph of my function, but I don't know what my function is. But pretend that pretend that I'm not given what my function is. I'm asked to tell something about its graph, and the only information I'm given is this. This is a differentiable function. Its derivative is increasing. Without knowing the function itself, what can you tell me about the shape of its graph? If you're given this information, its derivative is increasing. Okay, let's say that at this point C, or well, maybe I should not name the same point. At this point, the value of my function is over here, and its tangent line, whatever it is, it looks like this. Okay, now, the slope of this tangent line gives you the derivative. Okay, that's fine. Pretend that you move forward. You go over here. At this point, your function, the graph of your function also has a tangent line, and by the assumption that you are given, by the assumption that f prime is increasing, you know that the slope of the tangent line where the the slope of the tangent line at this point is greater than the slope of this guy. So you will have to see something like perhaps that. Now pretend that you do this for all possible points. Like you can't do this because there are like infinitely many points. There are actually uncountably many points. But pretend that you were able to do this. Pretend that you had this infinite power to do this for every possible point. Then you would basically see the following picture. At this point, let's say this is your tangent line. Over here, you would see a tangent line with higher slope and so on. And the graph of your function would look like this. Okay, so the tangent lines to the graph of your function, as x increases, their slopes would increase by the given assumption. So try to imagine this, like whatever your graph is, at this point is on a like at this x coordinate, this point is on your graph, and this is your tangent line. I'm gonna increase my x, and the slope is somehow supposed to go up. If this happens, you see that your graph is supposed to look like this. It's supposed to point up like this. And in that case, you see that your graph is concave up. And if f prime is decreasing, then these slopes are supposed to decrease. So you're going to see a concave down picture. So you're going to see a graph which basically points downwards like this. So let me draw some shapes. So a prototypical concave up graph looks like this. Okay, but this is also concave up, and this is also concave up. These things are all concave up, and prototypical concave down graphs look like this. Okay, so these are concave up, these are concave down. So let's take one of these graphs, and just by drawing certain tangent lines, you can see that as the x coordinate increases, the slope of the tangent line increases. Over here, the slope is negative. Over here, the slope is still negative, but it's bigger. Okay. So this is the definition of concave up and concave down. Let's define what it means for a point to be an inflection point. Now, when you look at graphs of functions that you run in practice, they're not always concave up or concave down. Sometimes they start concave up, then they become concave down, then they become concave up again, and so on. The points where the concavity changes are called inflection points, okay? So let me write down the definition for that. Okay, let f be differentiable on the interval AB. We say that f has an inflection point at x equals c. So the inflection point is c f of c on the graph if the following two conditions are satisfied. The graph of f y equals f of x admits a tangent line at this point C f of C, and maybe I should simply write x equals C, and the concavity of f on opposite sides of C are the concavities of f on opposite sides of C are different. Okay, so inflection points are points where the concavity changes, but we also require something else. You want your function to be nice. You want your function to behave nice at that point, meaning that there should be a tangent line. Okay, so let me give you like some examples. For example, if you take such a function like y equals x cubed looks like this, for example, you see that this point is an inflection point. Okay, why? Because at this point, first of all, I have a tangent line. This function is differentiable. Pretend that this is y equals x cubed and this is 0. I have a horizontal tangent line, so my function is differentiable. Now on left of this point, my function is concave down. On right, it's concave up. So its concavity changes at this point. Okay, so this by definition is an inflection point. But not every change in concavity means that you have an inflection point. For example, if you take this point, you see over here, my function is concave up. Over here, it's concave down. But at this point, there is no tangent line. This function is not differentiable here. So this is not an inflection point, not inflection point. Okay? On the other hand, like if you take a y equals cube root of x, it is going to look like this. Now, if you take the point 0, this function is still not differentiable at 0. But remember, differentiability and having a tangent line to the graph, they're almost the same thing, but not exactly the same. There's like one exception. If your function is differentiable, there is a non-vertical tangent line there. And if when you try to compute the derivative, you get a plus or minus infinity, then you have a vertical tangent line. Okay? So if you get that limit plus or minus infinity, your function is still not differentiable, yet there's a tangent line. This is an example. So this function does have a tangent line there, which is vertical. It's not differentiable there, but there's a tangent line, so it satisfies the first condition. And the concavity of the function changes at this point. On the left of this point, it's concave up, then on the right, it's concave down. So this is an inflection point, okay? So this is an inflection point. Okay, so far I have just introduced some definitions. So at this point, it should be obvious why we want to figure out where the function is concave up and down and where the inflection points are, because as you can see, that this will allow you to roughly sketch the graph of function. Okay, I mean, I know that in practice, most of you are going to use advanced math software such as MATLAB, Mathematica, things like that, Gebra, but you may have to end up like you may end up having to draw the graph of a function on your own, so you should know how to find these. Now, we're going to next focus on how to figure out where the function is concave up and concave down and where the inflection points are. The next theorem tells you the relationship between these notions and the second derivative. Okay? Okay. Let f be differentiable on the interval AB and C be a point in AB. Then, this theorem has three parts. The first part says that if the second derivative is positive on an interval, then f is concave up. Then the reason for this is that, okay, I can't write down the proof, but well, okay, I'll write down the proof. I was planning to say it in words, but I'm going to write it down. The reason for this is actually pretty, like, why this is true is pretty obvious. When I write it down, you'll see it. This directly follows from the definition and the fact that positive derivative means that your function is increasing. So, as a deal to this part, we have the second part, which says that if you see negative second derivative, then f is concave down. Now, I also have a third part. Let me name this ABC. If f has an inflection point at C, f has an inflection point at C, and the second derivative at C exists, then it should be 0. Okay? Now, you have to be careful about part C. I'm going to make some comments about that. Let me first prove this. Proof of, let's prove A and C. Now, suppose that f double prime of x is positive on AB, then since, you see, if you think of f double prime as the derivative of f prime, think of your f prime as your function g. If I tell you that, like, think of this as your g. If I tell you that g prime is positive on an interval, what can you tell me? It is increasing. So f prime is increasing, my f prime is increasing on AB, and so by definition, f is concave up. Remember, the definition of concave up is that your derivative is increasing. And so f is concave up. Concave up. On the interval AB. Okay? Part B, proof of part B is similar. You can guess what's going to happen. You're just going to flip the inequalities. Now, proof of part C. Okay. Suppose that f is an inflection point at x equals c and f double prime of c exists, then what does it mean for f to have an inflection point at c? It means that, first of all, there's a tangent line. Let me go up to definition. There's a tangent line at that point. And more important, the second part says that the concavity changes, okay? So the concavity on opposite sides of C are different. So if you have an inflection point here, you're concave up here, or concave down here, or concave down here, concave up here. In either case, what is happening is f prime is either increasing up to C and then decreasing, or decreasing up to C and then increasing. So then f prime is f prime has a maximum or minimum at x equals c. Why? At C, you see an inflection point over, like the concavity changes, so it's either concave up and concave down here, or concave down here, or concave up here. Concave up means that the derivative is increasing. Concave down means that the derivative is decreasing. So if you look at the derivative is increasing and decreasing. So in this case, it will have a local maximum. Or if you're in this case, if your function is concave down and concave down means that derivative is decreasing. Concave up means that derivative is increasing. So in this case, the derivative will have a local minimum. So in either case, you will see an extreme value. But remember, we learned a theorem. If you have an extreme value at a point, and if at that point your derivative exists, then that derivative has to be 0. Now, f prime has an extreme value at C. F prime has an extreme value at C. And its derivative, the derivative of f prime, which is f double prime, maybe I should just write like this. F prime has a maximum minimum at x equals c, and the derivative of this function at c exists. So the theorem we learned about where can extreme values occur. Remember, like if your function is an extreme value at a point, and if at that point the derivative exists, it has to be 0. F prime is an extreme value at c. The derivative of f prime at c exists, so this derivative should be 0. Okay, so that's the proof of this theorem. Now, this theorem is very useful. It tells you that, like, let's go back to the previous section. How did we figure out where a function increases and where a function decreases? Remember, we did these tables. We used the first derivative test. The first derivative test told us that, like, if the sign of my derivative is positive here, then it's increasing here, and if over here it's negative, it's decreasing. So I have a local maximum, and I had a similar thing for local minimum, and so on. This is kind of an analog for that, for concavity. It says that if you see positive second derivative, you are concave up. If you see a negative second derivative, then that means that you are concave down, okay? And pretend that you have some point where your function is concave up and then it's concave down, then the concavity changes. This will be an inflection point provided that you have a tangent line there, okay? So part A and part B, they're basically the analog of the first derivative test for concavity. Like instead of figuring out the intervals of increase and decrease, we figure out we figure out the intervals where the function is concave up and concave down. Part C is also very important. It tells you this. You may think of this as an analog of the theorem I just mentioned in the proof. Remember, if you see an extreme value, if you have an extreme value and if the derivative exists there, the derivative has to be 0. So this theorem tells you that if you're looking for extreme values, then you should look at critical points, because critical point, if you're not a singular point or an endpoint of the domain of your f, if you have an extreme value at a point where the derivative exists, the derivative will be 0. So your candidate points are the critical points. So that theorem tells us that the critical points are candidates for extreme values. This part C tells us that the points where second derivative 0 are candidates for inflection points. Okay? If you're an inflection point and the second derivative exists there, then it has to be 0. So this simply suggests that if you're trying to figure out where the inflection points are, just look at where the second derivative are, where the second derivative becomes 0. Now you have to be careful about the following. Warning. These two theorems that I just mentioned, they are not. They only work in one direction. They are not reversible. So, what do I mean by this? So, f has an extreme value at a point C, and f prime of C exists, implies that the derivative at that point is 0. Okay, we proved this right after mean value theorem, and I just told you that f has an inflection point at C, and f double prime of C exists, implies that the second derivative is 0. Now, in general, you cannot reverse these implications. Okay, just because you see 0 derivative at a point does not mean that at that point you will have a local max or local min. Here's an example. Here's an example. Y equals x cubed. Okay. Over here, if you compute the derivative at 0, it will be 0. So 0 is a critical point, but no local max or local min at x equals 0. Okay. Because up to 0, this function is increasing, then there's a horizontal tangent line, but after that it keeps increasing, so it's just increasing. Okay, so I have a critical point, but that doesn't give me an extreme value, and a counterexample to that can be easily found by this. These polynomials y equals x to the power n, where n is even and big. So let's choose 4. Okay, so f double prime of 0 is 0. If you compute the second derivative of this, it will give you 12x squared. So at 0, its value is 0, but no inflection point at x equals 0. Okay, so we don't have an inflection point. So just because you see that the first derivative is 0 does not mean that you have a local max or you have some extreme value. And just because you see second derivative is 0 at a point does not mean that that point is an inflection point. Okay, so these theorems only work in one direction. You have to be careful. This is why I kept saying these, like the points where the first derivative is 0 are candidates for the points where the extreme values occur, and the points where the second derivative 0 are candidates for inflection points. Okay, so let me check my notes. Well, I'm actually checking your book. So with that, I think it's time for us to solve a couple examples. Example. So find the intervals of increase and decrease and find intervals of increase and decrease, the extreme values, and the concavity of the function f of x equals 3 x to the power 5 minus 5 x to the power 3. Okay. Okay. So we're combining all the things that we learned in this lecture and in the previous lecture. So I'm given a nice polynomial, a fifth-degree polynomial. Don't worry, I chose it specifically so that when we take its first and second derivatives, things will factor out. Because in general, we're not expecting you to know how to factor a cubic equation or a fourth-degree equation or a fifth-degree equation. After which, actually, there are no general formulas. Okay, so we're supposed to find where this function increases and where this function decreases. We're supposed to figure out its extreme values, local min, local max, absolute min, absolute max, and we're supposed to figure out its concavity, meaning that, like when someone says find the concavity of a function, it means that figure out the intervals where it's concave up and where it's concave down. Okay. Now, let's take the first and second derivatives of this function, because we will be using these. So the first derivative of this function is a 15x to the power 4 minus 15x squared. So in 15x squared parentheses, I get a x squared minus 1. So I have 15x squared, x minus 1, x plus 1. So this is the first derivative. And if I take the second derivative of this guy, a 15x to the power 4 minus 15x to the power 2, I get 60x cubed minus 30x, and in 30x parentheses, this will give me 2x squared minus 1. Yes? No? Am I making a mistake? No, I don't think so. So let's take this 2 out as well. So let me write this as 60x, and then I'm going to have x squared minus 1/2, which is going to be x minus 1 over root 2, x plus 1 over root 2. Okay? Okay. Yeah, I'm checking whether there are any arithmetic mistakes, because it's going to create a problem actually if I made a mistake in the computations. Okay, these seem right. 60x cubed, 30x. Okay, these seem right. Okay. Thus, if I set the first derivative equal to 0, it gives me 3 points. X equals 0, 1, or minus 1. So these are my critical points. These are the points which make the first derivative 0. And if I set the second derivative equal to 0, I get that x equals 0, x equals 1 over root 2, or x equals minus 1 over root 2. Okay? Now, I'm not saying that these are the inflection points. These are the candidates for inflection points. If there's an inflection point, and if at that point second derivative exists, then it should be one of these guys. Okay? So let's do a table. Okay, so let me do the table over here. X, and the domain of this function is, well, I'm not given any specific domain, so I'm just going to pretend that it's the largest possible domain, which is minus infinity to infinity. And I'm going to put f prime here, f double prime here, and f here. Okay, now I have three critical points: -1, 0, -1, 0, 0, 1. At these points, the derivative is 0. Okay, and I have 3 points where the second derivative becomes 0. So over here it's 0, at 1 over root 2, which is somewhere over here. This is 0, and at -1 over root 2, which is somewhere over here, it is 0. Okay, now I'm going to figure out the signs of the first and second derivative. If x is less than -1, this is negative, this is negative, this is positive, negative, negative, positive, it's positive. If x is between -1 and 0, if you're between -1 and 0, this term will be now positive. This term will be, okay, I realized that when I watched yesterday's video, while pointing to some things on screen, I can actually see the pointer, but for some reason it doesn't record it, so I should actually underline this when I say here and here. So this term will be a positive. This term will be a negative if x is between -1 and 0, and this term is positive, so positive, negative, positive, it will be negative. Now, if x is between 0 and 1, this is positive, this is a still negative, and this is positive, so positive, negative, positive, negative. And if x is bigger than 1, this is positive, this is positive, this is positive, everything is positive, so it's positive. Okay, so at the moment, I know that by the first derivative test, my function is has a local my function is, first of all, increasing here, decreasing here, decreasing here, decreasing here, decreasing here, increasing here. So by the first derivative test, I see a local maximum at -1, and I see a local minimum at 1. Okay, so this is what I got from the first derivative test. Now let me fill out the table for the second derivative. Here is my second derivative, and if x is less than -1 over root 2, you see this is negative, this is negative, and this is negative, 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 negative. It gives you something negative. And if x is between -1 over root 2 and 0, this time this will be positive. This is still negative. This is still negative, 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 positive, positive. If x is between 0 and 1 over root 2, positive, and negative, positive, so it's negative. And if x is bigger than 1 over root 2, all these terms will be positive, so it's positive. Now, this term here, which I covered, tells me that in this interval, you see, I see negative second derivative, so my function is concave down. Okay. Over here, I see positive second derivative. My function is concave up. I see negative second derivative is concave down, and over here, I see positive second derivative is concave up. So I figured out the intervals of concavity. Now I'm going to look for inflection points. What do I need for inflection points? The concavity should first of all change, and my function should have a tangent line. Well, this is a differentiable function. It's differentiable everywhere. At every point it has a tangent line, so I should just look for points where the concavity changes. At this point, x equals minus 1 over root 2. The concavity changes from down to up, so it's an inflection point. Well, I have 3 of these, so maybe I should do it like this. At this point, the concavity changes. At this point, the concavity changes. And at this point, the concavity changes. All these 3 points, minus 1 over root 2, 0, 1 over root 2, these are inflection points. Okay? These are inflection points. Now, let me write down all that I have learned about this function. Remember what the question said? Find the intervals of the increase and decrease, the extreme values, the concavity. Okay, so f is increasing on the intervals minus infinity to minus 1 and 1 plus infinity. F is decreasing on the intervals minus 1 to 0 and no, minus 1 to 1. That's just it just keeps decreasing over here. Okay, so I figured out the intervals of increase and decrease. What about extreme values? F has a local maximum at x equals minus 1, and it has a local minimum at x equals 1. Okay, and f is concave up on the intervals minus 1 over root 2, 0, and let's say and 1 over root 2 infinity, and f is concave down on the intervals minus infinity to minus 1 over root 2 and one more interval 0, 1 over root 2. Okay, now using this data I can actually try to plot the graph of f, but I'm going to do one more thing. I'm asked to find the extreme values, not just the local extreme values. I found the local ones here, but are there global ones? Well, no. The reason is if you take the limit of f at infinity, it's going to be infinity, and if you take the limit of f at negative infinity, it's going to be negative infinity. So there are no absolute extreme values. Okay, my function goes up to infinity when x goes to infinity. It goes down to negative infinity when x goes to negative infinity. So it can get arbitrarily large values and arbitrarily small values. So it does not have an absolute max or absolute min. Now, using this data, using this table and using the data I just extracted from this table, I can actually plot the graph of this function. We have a separate section where we're gonna plot graphs of functions, but let me do one anyway. Let me plot the graph of this. Okay. So I have 5 points of interest. 0, 1 over root 2, 1, minus 1 over root 2 minus 1. Okay, and on left of minus 1, my function is increasing and it's concave down, and at minus 1 it will have a local maximum value. And what's the value of this function at minus 1? If you plug in minus 1, you're going to get minus 3 minus minus 5, sorry, a minus 3 minus minus 5, you're going to get 2. Okay, so the value of this function at this point is 2, and on left of it, it's concave. Look at this, it's concave down and it's increasing, so it's going to look like this. Okay, and then at minus 1 it is a local maximum. Afterwards it's going to start decreasing. It's still, as you can see over here, it is still concave down and it's decreasing. Okay, that's fine. And it's decreasing. Where's this function? No, it's over here. I think if you plug in minus 1 over root 2, you're going to get something positive. I'm not going to check that, so it's over here. Now, something interesting happens at a minus 1 over root 2. You see, after this, it starts decreasing. It's still concave down. At minus 1 over root 2, the concavity changes. I have an inflection point. It starts from, like, it was concave down and it becomes concave up. So it was concave down and it becomes concave up. It's still decreasing until 0. Okay, what happens at 0? Well, nothing happens at 0. It's not a local max, it's not a local min, but there is something happening at 0. I see a horizontal tangent line. Okay, so I see a horizontal tangent line here, so I have to be more careful. So over here the concavity changes. At 0 I see a horizontal tangent line, and afterwards, after 0, it's still going to keep decreasing in a concave down way. So at 0, actually something happens. I forgot to say that. 0 is an inflection point. It's not a local max or a local min, but it's an inflection point. So the concavity over here, the concavity was like down. It was down again. It was up. And at 0, the concavity actually changes. So after 0, it's going to decrease, but it's going to decrease in a concave down way. Over here you can see it. It's going to decrease in a concave down way until this point. At 1 over root 2, concavity changes again. Your function becomes concave up, as you can see here, but it's still decreasing. So it's decreasing in a concave up way. Okay, I need to undo what I did. I should write this over here, and my function becomes concave up, and it keeps decreasing until 1, where it will take the value minus 1, minus 2. Okay, and this is a local minimum. Now after this, the concavity is still up, and my function is increasing. And as x increases to infinity, my function increases to infinity, and x goes to negative infinity, my function goes to negative infinity. So it's going to roughly look like this. Now, let me show you a more accurate picture from Mathematica. Plot a 3 times x to the power 5 minus 5 times x to the power 3. And let's say that x is between a minus 2 and 2. That should be fine. Okay. This is the picture, okay? Like, it resembles what I tried to draw, though this is much better. As you can see, my function is concave down here. It's still concave down. Over here at a 1 over root 2, it changes its concavity to up. It's concave up now. And then at 0, I have another inflection point. It becomes concave down. So over here is concave down. It's still concave down until somewhere over here, at 1/√2, it becomes concave up. As you see over here, it just the concavity changes. It starts to curve in the other direction. So it becomes concave up, and then at 1 I have a local minimum, then afterwards it's still concave up and increasing. Okay, so this is the graph of this function. And as you can see, I was able to sketch this graph just from this table. Okay, so that's that. Okay, this tablet created a little problem for me. Okay, that's fine. Okay, so this question should be enough. As I said, like there will be recitation videos and you're gonna solve more questions, so don't worry about this. And when we cover a section 4.6 where we sketch graphs of functions, we will be doing this over and over again, so don't worry about me not solving more than one question about this at the moment. I mean, I will solve one more question, but in that question I will try to use the second derivative test to figure out local max and local min. Okay, what is the second derivative test? I just mentioned it. Remember the first derivative test. It tells you by looking at the sign of the first derivative, it tells you whether at a point you have a local maximum or local minimum. But it may not be always clear what that sign is. Like you have your critical point, you try to figure out whether it's a local max or a local min, but then you have to figure out the signs of the derivative on both sides. But maybe that's not that easy. There's another method called the second derivative test. It tells you the following. The second derivative test. Okay. Let me directly write down the definition. Let me directly write down the statement. If a f prime of z is 0, so you have a critical point, and f double prime of z is positive, then f has a local minimum. And if you flip this inequality, then you're going to get a local maximum, as you can guess. And okay, this tablet started not working properly again. And if the second derivative at c is 0, then the test fails. Then the test fails. Okay, so we have a sad smiley because the test failed. So let me prove let's name these A, B, and C. Let me prove A and C. But before I start the proof, let me tell you why this is useful. Now, this tells you whether a critical point is a local max or local min sometimes, not all the time. Pretend that you have a critical point. What you can do, like you want to figure out whether that's a local max or local min. So if you can figure out what happens on the left of that critical point and what happens on the right, like whether your function is increasing and decreasing on these sides, then by first derivative test, you can figure out whether that's a local max or local min. This is a second tool, okay, which uses the second derivative. This is why it's called the second derivative test. It tells you that if you have a critical point, just look at the second derivative there, okay? The second derivative there can be either positive, negative, or 0. If it's positive, your critical point is a local minimum. If it's negative, your critical point is a local maximum. Why? Like, you can actually pictorially, you can understand why this is the case. You have a critical point, you have a horizontal tangent line at this point. This is your C, you have a critical point, and the second derivative is positive. So around this, you're expecting your function to be concave up. If you see a horizontal tangent line, and if your function is concave up, this better be a local minimum, okay? And if the second derivative is a negative here, your graph is supposed to be concave down, and there's a horizontal tangent line, so you should have a local maximum here, okay? And if there's a third case, your second derivative may be 0 as well, just like your first derivative. In that case, you can't really say anything, okay? Now let me prove part A and part C of this, and then we're going to solve one more question regarding this. So suppose that, nope, I should select this. Suppose that f prime of C is 0 and f double prime of C is positive. Then we have that now E C plus H minus H equals, let me write down the whole equality, then I'm going to explain what's going on. Okay, so suppose that f prime of C is 0 and f double prime of C is positive. Okay, so this is my assumption, f double prime of C is positive. What is the definition of f double prime of C? What's the definition? It is, well, this is the derivative of f prime at C. So this is the limit definition of the derivative of f prime at C, f prime of C plus H minus f prime of C divided by H. And H goes to 0. I'm taking the limit of this quotient. Now, I assume that f prime of C is 0, so this is equal to that, f prime of C plus H divided by H as H goes to 0. Okay, so it's the limit of this quantity. Now, by assumption, this is given this number here is f double prime of C is positive, which means that this limit is positive. Okay, this limit is positive. And so, what can you tell me if this limit is positive? You can tell me that f prime of a C plus H is a positive for all sufficiently small positive H. And you see, if this limit is positive, you can deduce the following. Pretend that instead of sending H to 0, send H to 0 from right. Then this denominator is positive. The limit of the quotient is positive, which means that the numerator has to be positive. So this numerator has to be positive for all sufficiently small positive H. And similarly, pretend that H goes to 0 from left. Now H is negative. The denominator is negative. You're taking the limit of a quotient, but the limit of the quotient is positive. In order for this to happen, for sufficiently a small negative H, the numerator has to be negative as well. So this is negative for all sufficiently small negative h. Okay? It follows that a wait, what? For sufficiently small h, okay. Oh yeah. Okay. Yes. It follows that. Now, what's happening at the point C? Let's try to understand this. For sufficiently small h values, positive h values, I see positive derivative here, okay? So for sufficiently small h values, I see positive derivative here. So over here, I have positive derivative. Over here, I have positive derivative. So when I get very close to C, when I look at C plus h, when I get very close to C, I see positive derivative here, which means that my function is increasing over here. And for a very small negative h, when I look at this point C plus h, I will be on the left of C. And for very small h, I will be very close to C. And over here, I have negative derivative, meaning that my function is decreasing, okay? Now, the first derivative test tells me now that it follows from the first derivative test that what I wrote over here simply tells me that in a neighborhood of C, the following happens. On the right of C, the derivative is a positive. On the left of C, the derivative is negative. So what does the first derivative test tells you? The derivative goes from negative to positive. So I have a local minimum. Okay, so it follows that from the first derivative test that f has a local minimum at C. Okay, so that's the proof of part A. Now, a part B is similar. You can guess what's going to happen. The inequalities will be flipped, so I'm not going to write that down. Let me do the proof of part C. In part C, we should say that the test fails. C may be, F may have a local max, local min, or none at this point. Part C says that if the second derivative is also 0, you can't really say anything. Like, it may be a local max, it may be a local min, and it may be neither. So I should show you that all those three cases can happen so that you can't deduce anything, okay? Consider the maps f of x equals x cubed, g of x equals x to the power 4, and h of x equals minus x to the power 4. That's fine. Then, if you compute the first and second derivatives of these functions at 0, you will all get 0. But f does not have a local max or min at x equals 0. G does have a minimum at x equals 0, and h does have a local maximum at x equals 0. Now, let me explain what's going on. I wrote down three functions. The first one is y equals x cubed, like it looks like this. At 0, the first derivative is 0, the second derivative is 0. So if you try to apply the second derivative test, the second derivative is 0. So this test should fail, and like you should not be able to tell anything. Well, in this case, it's neither a local max, it's not a local max or local min. Okay, so you can see that the second derivative is 0, and it's not a local max or local min. In the second case, y equals x to the power 4, the function will look like this. At 0, the first derivative is 0, so it's a critical point. The second derivative is 0, it's a local max. So in this case, the second derivative becomes 0, but it's a local max. And in this third case, I just flip this. Now, at 0, I have a local max, okay? Instead of a local min, I have a local max. So what this shows is this. I have three cases. In all these three cases, I have a critical point, which is 0, and the second derivative becomes 0 at this critical point, which is also 0. And in all these three cases, different things happen. In the first one, the critical point is not a local max or local min. In the second one, it's a local min. In the third one, it's a local max. This shows you that if the second derivative is also 0 at your critical point, then you can't really say anything, okay? You can't say that it's a local max or local min, or you can say it's neither. It can be anything, okay? So that's that. Now let me solve one final question. Example where we're gonna see second derivative test in action. Okay, so in this question, what we're gonna do is we're gonna let f be we're going to let f be let f of x be the following map: x squared minus 3 times e to the power minus x, be defined on, so we're going to consider this on the interval -2 to 6, okay? The question is, find the extreme values of f on this interval -2 to 6. And let's also say that let's sketch the graph. Roughly sketch the graph. Roughly sketch the graph. Okay? Okay. So let's take the derivative of f, and let's take its second derivative as well, because we're going to be using the second derivative test. I mean, the point of this question is to illustrate to you the second derivative test. We have that f prime of x is, so this is a product, so I need to use the product rule for differentiation. I have derivative of the first one times the second one plus first one times the derivative of the second one. So in e to the power minus x parentheses, this is going to give me the x squared. Oh, there's a mistake. Derivative of the first one times second one plus first one times derivative of the second one. Derivative of e to the power minus x is e to the power minus x times -1. Okay, so if you take this to e to the power minus x parentheses, you are going to get a minus x squared plus 2x plus 3, which is going to factor as let's put this minus 1 out. So it's x squared minus 2x minus 3. So it's going to be x minus 3 x plus 1. It's going to factor like this. So this is the first derivative. And let's find the second derivative as well. So I am going to take the derivative of this term. I have to use product rule 2 times now. So let's take the derivative of this one. Derivative of the let's take derivative of this term. Derivative of the first one 2 times the second one e to the power minus x plus first one 2x times the derivative of the second one e to the power minus x times minus 1. So this is the derivative of the first term plus, now I'm going to differentiate this. A derivative of the first one 2x times second one e to the power minus x times minus 1 plus a first one x squared minus 3 times derivative of the second one e to the power minus x times minus 1 times minus 1 because of the chain rule, but minus 1 times minus 1 will be 1. So I have this. And if you take this to e to the power minus x parentheses, I think you are going to get, let's see, 2 minus 2x a minus 2x a plus x squared minus 3. So in e to the power minus x a parentheses, you get x squared minus 4x minus 1, okay, which does not easily factor, unfortunately. But I can find the roots of this, which I will. So let's find the critical points. First, f prime of x equals 0 gives us that x is 3 or minus 1. And f double prime of x equals 0 gives us that by the quadratic formula, this the roots of this polynomial, the roots of this second degree polynomial will be, let's see, minus b plus minus b squared minus 4ac will give you this. Okay, so minus 4ac divided by 2a, so it's going to be 2 plus minus you are going to get over here a root 20, which is a 2 root 5, and you're dividing by 2, so you can get root 5 here. Okay, so the roots of this polynomial are 2 plus root 5, 2 minus root 5. So we have this. And now I'm going to do my table like I did before. I mean, I don't have to do this in order to figure out the extreme values, by the way, but at the end, the question also asks, like, roughly sketch the graph, right? So I'm going to do this table, which will contain every piece of information that I need to draw the graph of this function on this interval. So my interval is minus 2, 6, and over here I'm gonna put f prime, over here I'm gonna put f double prime, and over here I'm gonna put f. So I have two critical points, a minus 1 and 3. Okay, and I have two possible candidates for inflection points. I don't know whether they're inflection points or not at the moment. One of them is over here, 2 minus root 5. This is something like, this is negative because root 5 is bigger than 2, but it's not less than minus 1, so it's over here. So it becomes 0 here, and 2 plus root 5 is something like 4.2, blah, blah, blah. So it's over here. Now, let's look at the sign of the first and second derivative. If x is between a minus 2 and minus 1, this term will be negative. This term will be negative, 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 positive. I see another negative sign here, so it's negative. This is positive, so I'm going to get a negative. Between minus 1 and 3, this term will be positive. this term will be negative. This is negative, so positive, negative, negative, you get positive. This is also positive, so this is positive. And between 3 and 6, both of these terms are positive. This is negative, this is positive, so this is negative, okay? And the second derivative, because I already factored this, so this is like x minus 2 minus root 5 and x plus 2 minus root 5. You can check that the sign of this will be over here positive, negative, positive, okay? So at the end, I get the following theta. My function is, the derivative is negative, it's decreasing here, it's concave up. It's increasing here, it's still concave up. It's increasing here, it's concave down. It is decreasing here, it is concave down, and it is decreasing here, it's concave up. Okay, now I can get the extreme values by the first derivative test or the second derivative test. Okay, now by the first derivative test, my function is decreasing, increasing, so I see a local minimum here. My function is increasing, decreasing, I see a local maximum here. Okay, and let me also check the endpoints as well. It's decreasing here, so this endpoint will be a local minimum, and this will be a local maximum. So this is by the first derivative test, but I can also get this by the second derivative test as follows. What are my critical points? 3m minus 1. I am going to plug this into the second derivative. F double prime of 3 is e to the power minus 3 times 9 minus 12 minus 1. This is going to give you e to the power minus 3 times a minus 4. This e to the power something is always positive, so this is negative. So I should have a local max at this point, which is the case. So by the second derivative test, f has a local max at x equals 3. Now I'm gonna plug in I'm gonna plug in the other critical point into the second derivative, and this will give me e to the power plus 1 times I plug in minus 1 here, 1 plus 4 minus 1, so e times 4, this is positive. So the second derivative becomes positive at this point. So f has a local minimum at x equals minus 1 by the second derivative test. Okay, so using the second derivative test, I figured out what kind of critical points I have. Now, I should note that observe that we also get this info from the table using the first derivative test. Okay, like you've already seen me doing this. Like before I applied the second derivative test, I already knew that at -1 I would have a local minimum, and at +3 I would have a local maximum. This is because, like, from the table I can just apply the first derivative test. This does not mean that second derivative test is unnecessary. Like I was able to fill in this table and figure out the sign of the first derivative. This is why the first derivative test worked. But maybe you don't want to do this table. Maybe like if I were only asked to figure out a classification of critical points, I wouldn't do this table. I would simply find these two critical points, 3 and -1, and I would plug them into the second derivative. That would be way shorter. The only reason I drew the table is that like in about 30 seconds, I'm gonna sketch the graph of this, okay? The point is, you can both use the first derivative test and the second derivative test, okay? There's a slight chance that the second derivative test doesn't work time to time because of the third case. Like when you plug in the critical point, you might get a f double prime as 0, in which case anything may happen. You actually have to analyze that specific case, which most of the time would require you to sketch the graph. So that's that. Now, let me sketch the graph of this roughly. Okay. Shapes, this. Let's make this, let's put it over here, x, y. Now my interval is a -2 to 6, and I have one point here, okay, let's put -2 over here, and -1 over here, and 2 minus √5 over here, and I have a 3 over here, 2 plus √5 over here. Okay. Now, what's the value of this function at -2? If you plug in -2, you're going to get 4 times e to the power something, so it's a positive number. The point is it's positive. It's somewhere over here. Okay. And then it's like in this interval, over here in this interval, it's decreasing in a concave up way, which means that let's see, and its value at a -1 is, if you plug in -1, you're going to get something negative, so it's going to take a negative value. So what's going to happen is it's going to decrease down to a negative value here in a concave up way. And then there is a local minimum at -1, so it's going to start increasing after -1. It is still concave up. Okay? It's still concave up. And if you plug in 2 minus √5, I guess you're going to get something negative. So let me put this -1 over here. Oops. Undo. So let me draw a better picture. So between -1 and 2 minus √5, it's increasing in a concave up way. Now something happens at 2 minus √5. You see an inflection point here, okay? Indeed, there are 2 inflection points. The concavity changes from positive to negative, okay? And if you plug in 0, you get something negative still, so it doesn't go really like that. It is going to go like this. You see, maybe I should just sketch the whole thing. It decreases down here in a concave. Okay, I am sorry for this. It decreases down the concave up way, and it increases in a concave up way. Over here, there's an inflection point. The concavity changes, so it's going to curve differently. So it's now concave down. At 0, it takes some negative value. And then after 0, what happens? Like, what happens? It's increasing and concave down up to the point 3. Okay? And at 3, the value of this function is a positive. So somewhere in between, it's going to take the value 0. Okay. Yes. I'm going to make this go further down in order to have some space. So it's decreasing over here. It's decreasing in a concave down way. And it's increasing concave up way, and it's increasing in a concave up way. The concavity changes now. It's increasing, but it's concave down, and it's gonna go like this. And at 3, something will happen. You will have a local max. So I have a local max here, and it's still concave down. It keeps being concave down until this point 2 plus root 5. And over here, the concavity changes. Okay, it becomes concave up instead of concave down. So the concavity changes. Everything will still be positive if you plug these into the function, and then it's concave up and increasing, and it's gonna go like this. Okay, so maybe I should do the following. Between -2 and -1, it's concave up, decreasing, so you have this. Between -1 and 2 minus root 5, it's increasing and concave up. So at -1, I have a local minimum. Between 2 minus root 5 and 3, it's increasing and concave down. This picture doesn't look concave down, does it? Well, that's my bad. It's supposed to look concave down here. And then between 3 and 2 plus root 5, it's going to decrease and it's still concave down. So at 3, I have a local max. And then between 2 plus root 5 and 6, it's going to increase and it's concave up. Okay? No. I mean, I basically can't read the table. It just says it is going to decrease. I don't know why I'd have that. After this point, it will still keep decreasing in a concave up way, okay? So I have an inflection point here. This is an inflection point, and this is another inflection point. So it's going to be concave up here, concave up in this region, concave down in this region, and concave up in this region. But after a 2 plus root 5, it's still going to decrease, okay? And I have a local maximum here, and I have a local minimum here and a local minimum here. Now, let me show you the actual graph of this function using Mathematica. So, x squared minus 3 times e to the power minus x between -2 and 6. Okay, this is the actual graph. Well, mine kind of resembles it, but apparently this point is supposed to be down below this, so yeah. Should I fix that? I can easily fix that. Okay, now it's fixed. I didn't plug in the values to the function and actually checked the values. This is why this happened, so don't worry. There's nothing wrong with our general procedure. So let's look at this actual graph. So it's decreasing here and it's concave up to our local minimum, which is at -1. So this is like -1, and it starts increasing. Did I say concave down? I am sorry. Between -2 and -1, it's concave up, it's decreasing. Between -1 and a 2 minus root 5, it's increasing and it's still concave up. At a 2 minus root 5, somewhere over here, something happens, as you can see from the picture. It changes its concavity, okay? It changes its concavity. It goes from being concave up to being concave down, and it keeps increasing as a concave down function until the point 3. At the point 3, which is over here, you see a local maximum, okay? It increases up to this point and then it starts decreasing. So you see a local max. And it's still concave down. It's still concave down up to 2 plus root 5, which is somewhere over here. Like you can't see it really in this picture, but it actually changes its concavity. It goes from being concave down to concave up. Okay, so this is how the actual picture looks like. This is my bad drawing. So that's that. And in this question, besides sketching the graph, we also saw the second derivative test in action. And you also have you should also keep in mind that I could have done this without the second derivative test, just using the first derivative test. But I just wanted you to see the second derivative test in action. So that's that. Okay. So this is the end of a section 4.5. Expect more videos. Stay safe.